This is a walkthrough of the solutions for the COS217 midterm from spring 2020, problem 3. In part A, the students were asked to reason about whether SimTable contains can simply call SimTable get and check if the value returned is not null. Consider what would happen if the symbol table allowed values to be null. For example, if using the key-value pair to represent just a set of keys, all with null values. In this case, a client might reasonably write this line of code to put into a given symbol table a key with its value being null. After doing so, the client might also reasonably then call SimTable contains on that symbol table, querying that key, and the client would expect that it does contain it. However, with this implementation, we would call get on a key. It would return null. We would check is null not equal to null. That would be a false, and so it would return false. That's a bug. The expected result would not be the same as the returned result, so in this case we cannot use that implementation, and our answer is no. In part B, the student was asked to determine the location of the compilation error and fix it. So let's consider this program. Line 3 looks suspicious because we're assigning a character literal into an int. However, this is perfectly okay. Character literals are really just 1-byte integers, and so when we assign it into an int, we are promoting that 1-byte int into a 4-byte int. This is totally okay. Line 5 might also look suspicious because we're assigning the address of an int to a void star. However, a void star is a pointer that can point at any type, so this too is totally okay. Line 7 is where the problem is. The issue here is that we are attempting to dereference a void pointer and use the data it points at. We can't do this because we have no idea what size that data is. We can fix this, however, by instructing the compiler to treat the void pointer as a pointer to a type with a well-defined size. We do so with a cast, which then, once we've cast to a pointer whose size we know, we can dereference it. So we'll start out by casting our void pointer to, in this case, an int star. Now, once we have that int star, we can dereference it. And that is a valid operation, so we can then do the rest of the printf just fine. In 3C, the student is again asked to find the bug in a program, though this time it is a logic error, not a compile time error. Let's trace the program with the given input and see what happens. We start off in main, so on the stack, we have main stack frame, which has P and Q. P gets initialized by calling getInt. So we call getInt. This is getInt stack frame. It has a local variable x. We call scanf to read into x. In our example, we read in 76. And then we return the address of x. This gets stored into P. So we have P points here. The next thing we do back in main, we've returned back to main, is we initialize Q by calling getInt again. So we have getInt stack frame, and it's going to read into x. And when it reads into x, it's actually a different function call. It just happens to use the same location. So it will read in 141, return that, and Q will point there. This gives us a good hint as to what the bug will be. The same location in memory stored the x from the first getInt function call and the x from the second getInt function call. We return the location rather than the int itself, and thus P and Q both pointed into the stack frame of the getInt function. However, after a function returns, its stack frame becomes inactive. We've seen exactly why, because the stack, we push and pop on and off of the stack as functions happen. With each new function gets to reuse that same stack frame location after a function is popped off the stack. So here P and Q both point to the same location. This now tells us what we can expect in the likely incorrect output. We very likely got 141 plus 141 equals 282. The bug in the program is returning address of a stack resident local variable. This also explains why fprintf would change the output of the program, because fprintf would similarly use the same location, and thus the location where x in getInt was stored on the stack is some other data used by fprintf, and that corrupts the value, whether it's 76 or 141, from the getInt calls.